on supercomputing and quantum computing, sponsored by AICTE Training and Learning Academy.
We are honored to welcome Professor Dr. Harish Mittal, who will be joining us for the first session titled Emerging Trends in Quantum Algorithms and Applications in AI.
First of all, thank you very much for inviting me to interact with you for this FDP. The topic of FDP is very recent and need of the hour, that is related to quantum computing, and I have selected the subtopic for today's talk, that is related to basically how we can use the quantum computing with AI. Artificial intelligence, we all know, right now crossing all boundaries. Specifically, if we talk about the breakthrough in past 2 years. Before 2 years back, the artificial intelligence was not too that much effective. But in recent 2 years, what we have seen that it has drastically changed the environment and how we deal with the artificial intelligence, and indeed we can say it is now really comparing with the human intelligence. Earlier we see only in definition that it mimic the working of the human being, but nowadays it is actually mimicking the human brain. And what exact issue now we are facing is the compute, the hardware, and there are some limitations of classical computing that are coming on the way, and these limitations we see that in near future we can overcome easily through the use of quantum computing and quantum mechanics, that is the base of the quantum computing. So today I will not talk much about the basics of quantum computing that you must have already discussed in the past 2 days. So I will just focus mainly on the things that are related to how we are going forward and making use of quantum computing along with the AI to overcome the challenges, what are the challenges, and how we overcome this challenges with the help of quantum computing. As I said that in classical computing we are having some challenges related to the compute as well as some complex problems that are still not achievable even through the advanced algorithm we are having, like NP-hard problems you have heard and studied. So these type of problems are a little bit difficult in handling through the normal computing, that we can easily deal with and solve with the. So we shall focus today's discussion over the basics of quantum computing, that are qubits, their superposition, the NISQ workflow, that is related to noise handling, relate the 4 major quantum algorithms that are used for AI tasks. Then we can just have an overview of recent hardware milestones that are being achieved by major companies, how we apply the quantum techniques to AI tasks, then evaluate the benefits in some key areas like logistics and healthcare as a case study, and identify the next resources for the implementation of the quantum computing. So let's start the discussion with a little bit comparison of classical versus quantum computing. We all know the classical computing that deals with the bits as 0 and 1. We are having only two states, either 0 or the 1 state. So if we are having n bits, then that basically belongs to n state in case of classical computing, and it is mainly serial computing and deterministic in nature, stable, predictable, well tested, and but the cons is that related to NP hard problems. This is the drawback of the classical computing. But comparatively, if we compare this with quantum computing, we are using, instead of bit, that is qubit. Qubit is basically that is comparable with classical bit. It makes the not beyond the 0 and 1. That means we are dealing with the superpositions. That means there are n number of states between 0 and 1. This is similar to the, if you toss a coin, so we see only head or tail, but in between the head of tail there are so many positions it takes during its flip and come back. So we are talking about these positions that are the intermediate positions. These n number of positions that we think about that are dealt with the quantum computing. So it deals with qubit, and the n qubits that relate to 2 raised to power n states, instead of here n bits relates to n state. So that simply means if there are 2 bits, then 4 states, 4 bits, 8 state, 8 bits, 128 states, and so on. So simple maths, 2 raised to power n states we shall be having. So this relates to parallel computing. There shall be either like we are having 2 bits, 0 and 1. So basically 2 की power n is not there, since we are having only 2 bits, 0 or 1. There is no other. N states are not there in classical computing, na? Basically only 0 and 1. That's why it's related to, otherwise you are okay. That's why it's raised to 2 raised to power n. So here it is not possible because we are having only 0 or 1 bit. There is no other bit. So we are achieving the parallel computing with the help of easily with the help of quantum computing and superpositions. Speeds are faster, sensitive to noise, but still it is maturing stage. Currently, as we could say that initially in the discussion I told that 3-4 years back, if we talk about artificial intelligence, that was in maturing stage. Now AI is matured stage, we can say, because AI is solving real world problems. If you talk about 4-5 years back, AI was not solving the real world problems, that was in a maturing state. So quantum computing is also, we can say, currently is not solving much of the real world problems. However, some of the big companies have invested a lot has been invested in the research, but still the theoretical aspect is more, practical aspect is less. Even though the companies like Google, IBM, they have developed the labs, they are practically implementing the quantum computing, quantum chips are also built up, but we are using the hybrid, you understand that it is a mix up of classical computing as well as quantum computing. We are right now not using pure quantum computing, we are using hybrid quantum computing, only because still the qubits processors are noisy. Noisy means they are prone to environment and they are prone to noises because of this very large number of states, they are not able to handle them properly, the large number of states, they are still noisy, so they are improving and in a hybrid state. Like bits, we handle the manipulations through gates, logic gates we use, and or not XOR. Similarly, in the quantum computing, we are having quantum gates and we manipulate and handle the logics through the quantum gates. So if we talk more about, just I have already discussed that like if we are having 1 qubit, then it raised to 2 states, 2 qubits, 4 states, 3 qubits, we are having 8 states and so on. So exponential state space is there because it is 2 raised to power n. So it will raise exponentially. But in case of classical, it is linear. So this is a simple workflow of a quantum computing system. We can say that it is a 5-step workflow. First one, we encode the problem. We formulate the problem space. That means convert the data to objectives into quantum states. We identify the quantum states through the qubits. We formulate the qubits and through the qubits we identify the quantum states. Then build the quantum circuit that I talked about, the quantum gates that are comparable with the normal logic gates in case of classical computing. Here we are having the quantum gates. So we are building the quantum circuits. Then in the similar fashion that we are running the normal classical computing through CPUs, and nowadays the AI programs we built through and run through the GPUs. But for the quantum we are having QPU, that is quantum processing units. So that is the advanced level of processing that facilitates the quantum processing. So we run the algorithms through the quantum processing unit QPU, or if it is for the experimentation purpose and the QPU is not available, then we process it through some simulators. We can simulate on the normal CPU or GPU through the simulator if it is for the experimentation purpose. So then we measure is similar that from the qubits to we come to the classical one. So we will convert the outputs to the classical outputs that are for the real time use, or we can say of normal use nature. This is just similar to we do in the fuzzy logic. We fuzzyfy, then last we defuzzyfy. Fuzzification, processing, then defuzzification. So here we again measure the qubits to classical 0 and 1 state, and then post process the results to interpret the bit strings and output classically. So this is a normal cycle of how the quantum program works today. NISQ machines, that is the machines that handle the noise easily, and we work in a hybrid fashion. The word NISQ stands for noisy intermediate scale quantum. Noisy intermediate scale quantum. So here two things are there. One is noisy qubits that I told. Second thing is intermediate scale. Noisy qubits that are prone to errors due to environment interference, lacking full error correction. That I told that currently the processors we are having, the hardware we are having is called as noisy because it is prone to environmental errors. When we scale the states to 2 raised to power n states, That means we come in a sense of superimposition. Then it may get some environmental error in handling the states, because states become too many. The number of states exponentially grows, then it may get some errors, and this is known as noisy qubits. The qubits become noisy. Intermediate scales, they have a limited number of qubits. Now the still if we say about the current hardware states, the number of qubits are limited up to I think thousands. We are having the hardware that supports up to 1000 qubits right now. And more specifically, if you say, if I talk about that 600 or 700 qubits, and in the current year, the IBM is expecting the hardware of crossing this 1000 limit with the 1100 qubits. So this is the intermediate scale. That's why noisy intermediate scale quantum state we are running right now. The state is noisy because the qubits are noisy, and the scale is intermediate. We are not still in a position to a higher scale. So the quantum is not currently being used to the full scale. The full scale is yet to come. Then we will see the drastic changes in the today's era of computing. Now I will come to some major algorithms that we used in quantum computing. Likewise, in every computing, like even if we do some normal computations, we use some algorithms. In artificial intelligence, if we use some algorithms. So for the quantum computing purpose, we use some algorithms. These four are the some major algorithms that we choose. There are so many other algorithms also. So I will not go in deep of the algorithms, how these process, just overview of the algorithms. One is Shor's algorithm, Grover's algorithm, QA, that is quantum approximate optimization, and VQE, that is variational quantum ion vector. First one, that is Shor's algorithm, that what it does, finds prime factors of big numbers, that helps in the finding the prime factors of big numbers easily, and it is mainly used in modern encryption problems like RSA. This problem is very old, but still it needs improvements, and that can be easily handled with this Shor's algorithm. Grover's algorithm, that mainly used for searching. The searching problems we use Grover's algorithm. If the space of searching, that means the quantum of searching is very large, then it is helpful in speed up the searching. Similarly, QA, that solves the tough optimization problems where we are having the problems related to optimization like routing problems, scheduling problems, in logistics, some financial problems. VQE, that is mainly used for estimating the molecular energy, that helpful in the domain like healthcare, where the drug discovery like problems can easily be solved with the VQE. Out of these four, we find that Grover's, QA, and VQE, these three are AI friendly algorithms that are more inclined towards the AI related problems like search problems, optimization problems, drug discovery problems. These are common AI problems that we deal with. So these three algorithms are more AI friendly algorithms, and Shor's algorithm is good, but it is not much practical, and error rates are also higher in case of Shor's algorithms. All these four offer the hybrid quantum classical workflow that we discuss, and that is the need of the current hour, because we are not yet into the full scale quantum. So the Grover's algorithm I discuss, that is mainly for searching problems. that deals with the search space problems. So this is a very classical and very short and simple example. Likewise, if I told that there are some drawers and I forget putting the key in one of the door and there is no number in the door, so simply what we will do, one by one we stretch the drawers and check in which drawer is the key. So total searching will be done in, if 4 drawers are there, 4 searching are there. There is no other way in a normal classical way. But in the quantum search, in the Grover's algorithm, what we do, we will offer the superposition, and we sometimes call it by intuition. We apply the human intervention like we do in addition to the classical search. Human intervention is like that. If I say that these are the 4 drawers, 2 are on the left, 2 are on the right. So my intuition is that normally I put the key in the left side. So what I will do, firstly I will search in 2 drawers that are in the left side. So my searching reduces to the half, 50%. So some intuition is also applied in addition to the random search. So instead of random searching, some intuition is added, and that intuition is added through the Grover's quantum search. So we use 2 terms, one is oracle and another is diffuser. Oracle is the finding that search space in which we are going to search by applying the intuition. Diffuser is applying that algorithm on the search. So like in the testing, normally we have studied test oracles. Test oracles are the cases that we create for testing. So similarly here we use the term oracle. This oracle is to create the search space, that is limited search space based on the, that means just like the 4 drawers are there, on the 2 we mark that these 2 are the what? Probabilities hai, so we mark them with some mark that we will be searching in these 2 first. So unki probability higher ho jayegi. So this is like that. So this is a simple graph that shows the classical search steps that go in a simple linear fashion, but here the search space is reduced in case of quantum search. So we reduce the search space with the help of this Grover's algorithm. And as well as reducing the search space, we are also offering the parallel computing. So the effect is quadruple, 4 times we can say. Second that we discuss is the VQE. VQE, that is variational quantum ion solver. The idea is also simpler here, that you can see classical optimizer, quantum optimizer, we use both. The output of classical optimizer goes to quantum optimizer. Quantum optimizer then optimize and give back to the classical optimizer. This process is repeated till we get the final solution. This is repetitive process till we get the final solution. So it is well suited for noisy quantum computers because it offloads much of the heavy lifting to the classical computer. Since we are having not the full scale quantum chips, that's why the half of the load is shifted to the classical computer. So that task that can be easily handled by the classical computer are done by the classical computer. The tasks that should be handled by the quantum computer, that are being handled by the quantum computer. So total burden is reduced. So this is the way we work. The key applications of this algorithm, as I told in the previous slide also, that was related to drug discovery like problems. So we can say the quantum chemistry we can use, material science problems we can use, that is designing the novel materials also, optimization problems like solving complex optimization tasks we can use it. So there are so many areas in which this algorithm may be applied. Third that we discussed was QAOA, that is quantum optimization in the real world. It solves the problems that we call like NP hard problems also. In the classical domain, we call some problems at the NP hard problems, very complex problems. These problems can be solved with this algorithms. And this is mainly suited for the combinational problems where the combinations are used. Dover's algorithm was mainly for the searching related problems. Here it is related to optimization problems. Whenever we are having some combinations, we are having some optimization problems. How to optimize these combinations. So the optimization problems that we deal with this QAOA method. So it is also designed for NISQ hardware. It uses the problem Hamiltonian and mixer Hamiltonian, and the problems that we solve are vehicle routing problem, task scheduling problem, inventory optimization problem, financial scheduling problems. Wherever some scheduling and optimization is required, we can use this algorithm. Whatsoever the problem is, wherever we need some scheduling or optimization, we can use this algorithm. With all this, if we keep together the algorithms, the hardware, we can come to quantum machine learning. So from the normal machine learning, we switch to quantum machine learning. So that combines the quantum computing with normal machine learning to process data and learn faster. This is the simple use. In addition to our normal machine learning algorithms, we apply the quantum computing. We make use of quantum hardware. We make use of quantum algorithms for the purpose, and the benefits of using qubits. So it uses the qubits for data processing, employs quantum algorithm for AI tasks like pattern recognition task or any other task. We use this quantum algorithms, and we use hybrid quantum classical approach. That hybrid always I state in every slide, that along with the classical computing we are using it. This could solve the AI problems beyond the classical capabilities and unlocks the breakthroughs in the science, finance, and most of the areas like healthcare and other areas. The challenges are the same that we already discussed: noise, scale. Two challenges that are universal challenge nowadays for this quantum computing: noise and scale. The application we already discussed for the quantum machine learning, that is drug and material discovery, financial modeling, complex data analysis. If we are having messy data sets or AI capabilities are being limited due to the massive data sets and the compute issue that normally occurs while training the machine learning or deep learning. Specifically, if we are using the deep learning algorithms and we are dealing with a large scale of data set, the major problem comes here with the compute. That means the training time is very large, or sometimes the training fails. That problems can easily be handled with this hybrid approach. So QMLs aims to solve AI problems that are currently impossible for even the most powerful classical supercomputers. Two targets or two objectives are there. One objective is that we solve the problem more efficiently, more fast. Second objective is there that we solve the problems that are currently difficult to solve. So two objectives, one is to fasten the process, second is if some of the problem is currently not solvable, then we solve that. So we are currently believing that in near future, like maybe in 1 year or 2 years, we will be at a breakthrough position where we shift from the current AI models to quantum AI models, and the results will be more than our imagination, because current results of AI is also beyond the imagination. 3-4 years we were not imagining that AI will do the things that currently it is doing. So we believe that in the near future it will also break through the boundaries, and the results shall be even more better than we expect. If we talk about the current state of the hardware and the research that is going on in the quantum hardware right now, if we talk about the 24-25 position, the IBM has released 127 qubit Eagle system, 433 qubit Osprey system, and as I told that it is well behind the 1000 target still. Not 1000 qubits are crossed, but it is targeting 1121 qubit Condor system very in soon. It may be in the current year or beginning of the next year. Similarly, IOMQ organization that already started some commercial contracts with like US Air Force, Hyundai, Airbus for the quantum systems. Neutron atoms, that is a large scale 2D qubit arrays are framed already, and flexible connectivity and high parallelism is achieved. So this is the current state that still it is not, we can say that right now we are not only in the theoretical state, we are already achieved many practical states, and industry and the government organization is adapting toward the quantum computing. Currently India is investing very heavily on the quantum computing, and it is spending a lot on the research. So soon as we can see that we are going to enter in the 1000 plus qubit era. As soon as we will this will be achieved 1121 qubit Condor, or other organizations are working on that to achieve this 1000 plus qubit systems. So 1000 plus, if we talk about 1000 plus qubit systems, that means 2 raised to power 1000 states are possible. So that if we say about exponential values, that will be a very high number. So that's why it is still difficult to achieve, but in near future it is, or you can say very soon it can be achieved. So this is a hybrid workflow, that is classical plus quantum AI. We start with classical machine learning system. We prepare some parameters, that is hyperparameters we talk about. Then we use the quantum circuit execution. We execute the algorithms through the quantum circuits. We get them optimized through the normal optimization algorithms we already have in the machine learning. Again, go to the quantum circuit, again execution, the learning process continues till we get the desired results, and or the loss is optimized, we can say. The optimizer is used to optimizing the loss, and when we achieve the accuracy, the desired level of accuracy, then we exit from the system. So this is simple and similar to the classical AI pipeline, just we introduce the quantum task in between. Normal machine learning, we just introduce the quantum task, mainly the quantum hardware that works here. And for the utilizing that quantum hardware, we use some quantum algorithms and some quantum gates for this circuit breaking building and giving the inputs and handling the outputs from the quantum system. So as we discussed in the earlier slides, the two key areas in which we find that quantum computing is very much useful is, one of the area is healthcare, another is the logistics. So if we talk about healthcare, two case study I have chosen. One is drug discovery, another is diagnostics. Drug discovery is sometimes related to the chemical side research. Diagnostics are just like we do many research in AI and machine learning that is related to diagnosing some problem based on the MRI images, based on the brain MRI, based on other X-rays, or combining some of the parameters. So these diagnostic problems and the drug discovery problems, we can easily deal with these quantum systems. For example, if we talk about drug discovery with VQE, then VQE algorithm can simulate the ground state energy of the molecules, then classical simulation. Then quantum computing model uses the Hamiltonians that allows the precise compound screening of the molecules. And the use cases are protein ligand binding affinity estimation, accelerate the early stage drug discovery, and material design. So we discover new drugs very easily with the help of this system. If we talk about the diagnostics with the quantum machine learning, then we can use the quantum enhanced classifiers. We can use quantum kernel methods to map data into high dimensional spaces. Then outperforms the classical SVMs. So if we talk about the quantum kernel method to map data into high dimensional spaces, so this is the problem normally we face in the normal classical computing. The using high dimensional space like 4 dimension, 3 dimension are normally used. But if we go beyond these, then it is very difficult. In case of normal classical computing, 2 dimension, 3 dimension, 4 dimension, we can easily deal. But if we go beyond that, then it is a problem that can be handled through this. So classical examples include the pneumonia detection, genetic mutation, EEG pattern classification, any type of classification or discovery problem that can be taken care very easily, where the data set for training is very large, space basically the dimensions, number of parameters are long, or the total number of parameters are higher, then we go for this. Similarly, in case of logistic problems, that is we can use QAOA that we discussed already. The QAOA, the quantum approximate optimization algorithm for the scheduling routing problems. logistic problems have the challenge like vehicle routing problem, delivery time, scheduling, supply chain problem, warehouse resource allocation problems. These problems, if we talk about in general, that are not seems to be very hard problems, but for the large scale, if you consider the problems like scheduling the Amazon warehouses that are spread across the world, and of a very large scale systems are there, so the problems become the hard. If the scale is not big, then these are the simple problems, but due to the scale of these logistic issues, then these problems are very hard, and we can solve them with the quantum advantage. Some of the companies have already started using these systems like Volkswagen, DHL, Amazon. These are already implementing these quantum systems. Like Volkswagen has used for taxi route optimization, DHL for the supply optimization, Amazon also using the research and warehouse scheduling through the quantum computing already. So already the things are in practice. These are some of the quantum platforms we can use for quantum research and softwares, and as well as we can try implementing some of the quantum computing systems. Like IBM is offering QSkit, that is open source SDK. AWS Bracket, that Amazon is offering. Penny Lake by Gendu. So these are openly available systems that are normally in use for quantum computing purpose. You can easily use. If we talk about QSkit, then it is best for circuit, VQE algorithm, QSVM algorithms, and it is free to access through IBM Cloud. AWS Bracket, that allows for multi-hardware access, and it takes the cost based on the use. Penny is also free and open source, that is best for using the quantum machine learning, PyTorch, TensorFlow along with the quantum computing. So Penny is very good option. So the final takeaway from the today's discussion is that still we are having in the state where we are facing two problems, that is one is noise, another is scale. So currently we are in the state of hybrid systems, that is classical systems along with the quantum systems. The best match of quantum system with the current AI models and machine learning models, deep learning models is there. If we combine these two techniques, then it will be a very good breakthrough, and we can achieve very fast speeds as well as accuracies, and will be able to handle the things that currently we are finding it difficult. So quantum magic, we can call it. It's a math with inference. And healthcare and logistics basically I choose, but this is not limited to healthcare logistics. We can apply in any domain, any area where there is a need as per the algorithms. So this is all from my side. If you would like to discuss anything, it is great pleasure for me.